Okay, so hi everyone. So good morning all. So first of all, let me know whether audio and video everything is clear. So let me know if audio and video everything is clear. Hello. So first of all, let me know whether audio and video everything is clear here. So if I get some confirmation, then we can start our session, right? Okay. So I hope audio and video everything is clear, right? I hope so, right? Okay. So if there is any problem, you can give some comment in chat box, right? So I hope everything is clear. So in this session, so we are going to cover the waveguides part, right, and antenna arrays. So these are the two topics that we are going to cover in this session here, waveguides and antenna arrays, right? Okay. So now see here. See, in rectangular waveguides here, so mainly we are going to talk about rectangular waveguides. So rectangular waveguides. So just I am going to do the revision here. So whatever that is important in case of rectangular waveguides, only those things we are going to see, right? Okay. So see here how I can construct a rectangular waveguide here. So a rectangular waveguide is going to have how many conducting plates here? It is going to have 4 conducting plates, right? So it is going to have 4 conducting plates. Right? Okay. So this is the broader dimension of the waveguide, and this is the shorter dimension of the waveguide. So I am calling this A as what here? A as a broader dimension, and this B is nothing but a shorter dimension. Shorter dimension of the waveguide. Okay. So now see here. This axis I am considering as this is a shorter dimension. Okay, so this is the cross section of the waveguide. Okay, so this is called as a broader dimension, and this side I am calling it as what? Shorter dimension. So here always remember that here in general we are going to consider A greater than what? A greater than B. Okay. So on this side, this axis I am considering as a x axis, and this axis this axis I am considering as y axis, right? So this axis I am considering as y axis. So this axis I am considering as z axis. okay, z axis, right. So z axis is going into the board here. So this is into the board. So x axis is pointing in this direction, y axis is pointing in this direction. So if you do x cross y, okay, positive z axis is going to point into the board. So here positive z axis is pointing into the board, right. Okay. So here how many conducting plates we are having here? Here how many conducting plates we are having? We are having side one conducting plate. So here another side you are having another conducting plate. On the bottom you are having one conducting plate, and on the top you are having another conducting plate. So we are assuming all these four conducting plates are perfect conducting plates here. So we are having four perfect conducting plates. We are having four perfect conducting plates, or you can say that so these plates are acting like an interface between this medium and outside medium. Okay. Okay. So I can say we are having four perfect conducting interfaces of this waveguide, right. So what are those four conducting plates here? Where they have placed? Tell me. So here this location, let us say this location is 0, 0. So this is x axis, this is y axis, and this is z axis, right. Okay. Okay. So at this location, what is x value? Tell me. At this location, what is x value? X value is equal to 0. So as you move along this direction, x value is going to increase. So at this location, x is equal to a, right, and at this location x is equal to 0, right. So that means on this conducting plate here, so this conducting plate represents what here? This represents a YZ plane. So YZ plane, that is placed at what? X is equal to 0. So wherever you move on this plane, x value will be equivalent to what? 0. Only y and z are going to vary, but x will remain same as you move on this conducting plate, right. Okay. So this is nothing but YZ plane. This is nothing but YZ plane, that is placed at what? That is placed at x equal to 0 location. So we can call this as x is equal to 0 plane or YZ plane, right. Okay. Okay. Right. So next, as you move along this x direction, this x value is going to increase, and at this location x value is equal to what? A, right. Okay. So at x equal to a, you have placed another YZ plane here. So this is nothing but what? This is nothing but another YZ plane, that is placed at what? That is placed at x equal to what? X equal to a, right. Okay. And you are having similarly two conducting plates at the bottom and at the top. So at the bottom, so from if you move from bottom to top, what is the what is going to vary here? As you move from bottom to top, y is going to vary, right. So at this location, so the bottom plane represents what? Y equal to 0 plane. Yes or no? So on the bottom plate, if you move here, if you move on the bottom plate, what are going to vary? So x is going to vary and z is going to vary. So x and z. So bottom plate represents what here? Zx plane, which is placed at y equal to 0, right. Okay. So this bottom plate represents what here? Zx plane, which is placed at x equal to what? Which is placed at y equal to what? Y equal to 0, right. So y is constant over this plane, right. Next, similarly at the top, what is the plate? What is the conducting plate that is placed here? So this is also nothing but what? At the top, what are variables here? X is variable and z is variable. Understood? So this represents another Zx plane, which is placed at a location of what? Y equal to b. So this conducting plate, this top plate is nothing but what? Is nothing but y equal to b. Y equal to b. So I'll write here. Okay. So y equal to b. So that is this is another Zx plane. This is another Zx plane, right. Okay. Okay. So you are having four conducting plates, sides 2 plates and bottom 1 plate and top another plate. So we are having totally 4 conducting plates. So one is placed at what? One is placed at x equal to 0 and another is placed at x equal to a, right. And 2 more conducting plates you are having. One is placed at y equal to 0 and another is placed at what? Y equal to b, right. Okay. Okay. So now see here. So I hope you know the boundary conditions here. I hope you know the boundary conditions. See, boundary conditions are going to play a very important role in dealing with what? In dealing with waveguides, right? See here, if you are having a perfect conducting interface here, let us assume this is the perfect conducting interface here. So let us say this is the perfect conducting interface, So here you are having medium 1 and here you are having medium 2. Okay, so this is acting like in between these two medium you are having a perfect conducting interface. So perfect conducting interface means the conductivity of this one is equivalent to what? It is equivalent to infinity. The conductivity of this one is equivalent to infinity. Right. Okay. So which means the skin depth of this perfect conducting interface here for this material. Okay. For this perfect conducting interface, what is the skin depth here? Skin depth is equivalent to what? Skin depth is equivalent to. So since it is perfect conducting interface, it is acting like what? Good conducting medium. So for a good conducting medium, what is the skin depth here? Skin depth is equivalent to 1 by square root of what? Pi f into mu sigma. Okay, but for this we are assuming this as a perfect conducting interface. So if it is a perfect conducting interface, then sigma tends to what? Infinity, which means delta is equal to what? 0. So that means the skin depth of this perfect conducting interface is equal to 0. So which means no fields can penetrate through this perfect conducting interface. Yes or no? Okay, so skin depth is equal to 0 means what here? No fields can penetrate inside this perfect conducting interface. So whatever the fields that are going to incident on this perfect conducting interface, so the total field has to get reflected back from the perfect conducting interface. Yes or no? Okay, so no fields can penetrate into medium 2 here because this is going to block the fields that are propagating from medium 1 to medium 2. So whatever the wave that is incident on this perfect conducting interface, the total wave is going to get reflected back into the same medium. Understood? So no fields can penetrate into the second medium. So this is acting like a blockage for the fields to propagate from medium 1 to medium 2. So if I consider this as the normal, this is the normal to the interface. So if the wave is incident here, let us say if the wave is incident on this perfect conducting interface, what will happen? No fields can penetrate it through this perfect conducting interface. So whatever that is incident, that will be completely reflected back. So in medium 1, what you are going to have? You are going to have incident wave, and also you are going to have what? You are going to have reflected wave, right? Okay, so there is no wave here there is no wave that is penetrating into medium 2. So if there is no wave means no electric field and no magnetic field here. So in this medium there will be no fields, that are penetrating into this medium, right? So in the same medium, what you are having here? Incident wave as well as what? Reflected wave. So the superposition of this incident wave and reflected wave is going to form what? Is going to form a traveling wave, incident wave and reflected wave. The superposition of this incident wave and reflected wave is going to form what? Standing wave pattern. Okay, now if suppose if I place another conducting interface here, if I place here another conducting interface here, let us say I have placed some other conducting interface. So this is perfect conducting interface. So then what will happen? So whatever the wave that is incident here, so this is the reflected wave, so it is going to incident on this perfect conducting interface. So it is going to block the wave to propagate to the other side. So whatever that is incident here, so for this one also skin depth is equal to what? 0. Yes or no? No fields can penetrate to this perfect conducting interface. So whatever the wave that is incident, that will be completely what? That will be completely again reflected back. Okay, so if suppose this perfect conducting interface is extending up to infinity like this, right? Then what will happen? Whatever the wave that is incident here, that is completely reflected back, and whatever the wave that is incident here, it gets completely reflected back. Yes or no? And whatever the wave that is incident here, that will be completely reflected back. So which means you are trapping this electromagnetic wave between these two conducting plates. Yes or no here? So, and between these two conducting plates, since you are having both incident wave as well as reflected wave, you can see a standing wave pattern. You can see a standing wave pattern between these two conducting plates. Yes or no? So, you are going to have a standing wave pattern. You can see a standing wave pattern between what? Between these two conducting plates, right? And what is the net propagation of the wave here? So, it is propagating like this, and again it gets reflected, it is propagating like this, again it's get reflected and propagating like this. Yes or no? So, but the overall, the net propagation here, actually speaking, it is zigzag path, okay, but the net propagation of the wave is in which direction? It is in this direction or not? Yes or no? So, the net propagation of the wave is in this direction, that is along the plates, right? So, you are going to have the traveling wave pattern here. The net propagation of the wave is along the plates like this. Understood? So, that means you are going to have the traveling wave pattern in this direction. Okay. So, that means net propagation of the wave, net propagation of wave is in this direction, and standing wave pattern is going to present between what? Between the two plates. So, along the plates you are going to have the traveling wave pattern, and between the plates what you are going to have? You are going to have the standing wave pattern. Understood? Okay. So, I have trapped the electromagnetic wave between what? Between these two conducting plates, right? Okay. Okay. So, whenever you trap the electromagnetic wave between two conducting plates, what you are going to get? You are going to get a standing wave pattern between the two conducting plates, and net propagation will be along the conducting plates. That is, the along the net propagation direction, you are going to have what? You are going to have the traveling wave pattern. Okay. So, here after all we are designing this rectangular waveguide with what? With 4 conducting plates here. We are having 4 conducting plates. So, just now we have seen that between any 2 conducting plates, you are going to have what? A standing wave pattern, and along the conducting plates, you are going to have what? The net propagation of the wave. So, here along the conducting plates, that is this is the conducting plate, this is the conducting plate, this is the conducting plates. Yes or no? So, if you move along the conducting plates, you are going to move along what? Z direction. So, here the net propagation of the wave will be in which direction here? Net propagation of the wave will be in Z direction. Net propagation will be in Z direction, and between these 2 conducting plates here, between any 2 conducting plates, since you are going to have both incident wave as well as reflected wave, you are going to see what? Superposition of these 2 waves, which is going to form the standing wave pattern. So, between this x equal to 0 and x equal to a, you are going to have what? You are going to have one standing wave pattern, right? And between y equal to 0 and y equal to b, so between these 2 conducting plates, you are going to have what? You are going to have another standing wave pattern, right? Okay. So, between these 2 conducting plates, you must have what? You must have another standing wave pattern. Okay. Between these 2 plates, you must have another standing wave pattern. Between these 2 plates, you must have another standing wave pattern, and the net propagation of the wave will be what? Will be along the plates, that is in Z direction. Okay. So, remember that in throughout waveguides topic here, all the parameters, that is phase constant and phase velocity, group velocity, so all these parameters, guided wavelength, so all these parameters are defined along the direction of what? Along the direction of net propagation. Okay. So, that is very, very important here, right? So, all the parameters, you can make a note here. So, all the parameters are defined, along what? Along net propagation direction, Okay. So, almost all the parameters are going to define along what here? Along the net propagation direction, that is along Z direction here, right? Okay. Okay. So, now see here. Next, see here. we know from the boundary conditions here, from the boundary conditions, right? So we know that boundary conditions, that is the first one is the difference between the normal components of electric flux density is compensated by the surface charge densities that are present at the interface. Yes or no? So the difference between normal components of electric flux density is compensated or is equivalent to what? Is equivalent to the surface charge densities that are present at the interface, right? So that means if you take an interface here, right? Okay, if you take some interface between the two medium, so let us say this is medium 1 and let us say this is medium 2, right? So at let us say this is z is equal to 0 interface, then this will become what? Normal to the interface, that is z axis, right? Okay, okay. Now see here. Now let us consider this is at z equal to 0 minus and this is at z equal to 0 plus. So whenever the fields are propagating from medium 1 to medium 2 here. So let us say in medium 1 the normal component of electric flux density is dn1, and whenever it is propagating from 0 minus to 0 plus, so let us consider at 0 plus the normal component of electric flux density is dn2. Okay, so here there exists some difference between this dn1 and dn2, which means dn2 is not same as dn1 here. So as this normal component of electric flux density propagate from 0 minus to 0 plus, so there is some changes are occurring exactly at the interface. So because of that change occurring at the interface, you are going to see some different normal component of electric flux density here. Okay, so that's why I am representing here with dn2. So there exists, both are not same here. Okay, there exists some difference between this dn1 and dn2. So the difference between these two is compensated by what? Is equivalent to or it is compensated by the surface charge densities that is present on the interface. Right, so which means I can say this as the normal component of electric flux density is not continuous across the interface. It is discontinuous across the interface. Yes or no? So if it is continuous means what here? Whatever that you are going to see at 0 minus, the same thing you have to see at 0 plus. Then only you can say it is continuous. Okay, but here you are having some different field, and at 0 plus you are having some other different field. So there is a discontinuity of the normal component of electric flux density as you move from 0 minus to 0 plus. Right, so that discontinuity is compensated by what? Is compensated by, or that difference between dn1 and dn2 is compensated by the surface charge densities that are present at the interface. Right, okay. Okay, next similarly if you consider the second boundary condition, so that is bn1 difference bn2 is always equivalent to what? Is always equivalent to 0, which means bn1 is equivalent to what? Bn2. So which means the normal component of magnetic flux density are always continuous across the interface. So if you see here bn1 here, if you see here bn1, so here bn2. Okay, so here bn1 will be same as what? Will be same as bn2. Right, so whatever the magnetic flux density, normal component of magnetic flux density that you are going to see just before the interface, that is at 0 minus, the same magnetic flux density you are going to see at z equal to 0 plus also, which means this normal component of magnetic flux density is continuous across the interface. Right, so this is the second boundary condition here. Right, okay. Next, the third boundary condition we are having is the tangential component of electric field intensity is always continuous across the interface here. So similarly, if you consider the tangential component of electric field intensity, so that is if you consider ET1 here, so if you consider here ET2, okay, so here ET1 will be always equivalent to what? Will be always equivalent to ET2. So here T1 and T2 represents what? Tangential. T means here subscript C, T represents tangential. Okay, so the tangential component of electric field intensity is continuous across the interface here. So whatever the tangential component of electric field that you are going to see at this side of the interface, the same field you are going to see at this side of the interface also. So that is ET1 is equivalent to what? ET2. right? Okay, next you are having another boundary condition, that is fourth boundary condition. So that is the difference between the tangential component of magnetic field intensity is compensated by the surface current densities that are present at the interface. Okay, so here the tangential component of magnetic field intensity are not continuous across the interface here. Okay, so that's what you have to understand. So there exists some difference between HT1 and HT2. That difference is compensated by the surface current densities that are present at the interface. Okay, so whatever the tangential component of magnetic field intensity that is present at 0 minus, you are not going to see the same tangential component of magnetic field intensity at 0 plus. So here HT2 is not same as what? HT1. There exists some discontinuity between HT2 and HT1, right? Okay, or I can say there exists some discontinuity across the interface here, right? Both are not continuous, right? Okay, so here also dN2 is not same as what? dN1. So here dN1 difference dN2 is equivalent to rho s, and here HT1 difference HT2 is equivalent to what? Is equivalent to Js, right? Okay, okay, so these are the boundary conditions at the interface here. These are the boundary conditions at the interface. Now, if I consider this interface, as perfect conducting interface, then what will happen? We know that if it is a perfect conducting interface, then no fields can penetrate into the other medium. Yes or no? In that case, what will happen? This dN2 will become what? This dN2 will become 0. All the field components in medium 2 will become what? Will become 0. Yes or no here? Okay, because no fields can penetrate into this medium 2, because you are having what? You are having here a perfect conducting interface. So just now we have seen that for a perfect conducting interface, the skin depth is equivalent to what? Is equivalent to 0. So which means no fields can penetrate into this perfect conducting interface. So whatever the fields that are incident here, that has to reflected back. No fields are going to penetrate into the perfect conducting interface. So that's why you are not going to see any fields in this medium here. So all fields in this medium will become equivalent to what? Equivalent to 0. So which means here I can make here dN2 is equivalent to 0, bN2 is equivalent to 0, ET2 is equivalent to 0, HT2 is equivalent to 0. Right, so all the field components will become equivalent to 0. So in the boundary conditions means you are writing what is happening to the field components just before the boundary and just after the boundary. Okay, so exactly at the boundary you are writing the boundary conditions. So how the field components are related exactly at 0 minus and 0 plus. Okay, so that relations is given by what? Boundary conditions. What actually happening at the boundary? So that is given by the boundary conditions, right? Okay, so if you place between medium 1 and medium 2, if you place a perfect conducting interface, all the fields in medium 2 will become equivalent to what? Will become equivalent to 0. So which means here in the boundary conditions you can replace dN2 equal to 0, bN2 equal to 0, right? bN2 equal to 0, ET2 equal to 0, JS equal to, sorry, not JS, HT2. Okay, HT2 equivalent to 0. So if you put all the field components in medium 2 equal to 0, then the boundary conditions at a perfect conducting interface here. So what you are going to get? Boundary conditions at perfect conducting interface. So all the field components at 0 plus will become equal to 0. So which means the first boundary condition you are going to get dN1 is equivalent to what? Rho s. dN2 will become 0. So replace dN2 equal to 0, you will get dN1 equal to rho s, and bN1 equal to 0, ET1 equal to 0, and HT1 is equal to Js. Yes or no? Okay, so these are the boundary conditions that you are going to get here. So at the perfect conducting interface, so dN1 is equal to rho s, and then bN1 is equal to 0, and then the third one ET1 is equivalent to 0, and the fourth one, that is HT1 is equivalent to what? Is equivalent to Js. Okay, now if you observe here, the tangential component of electric field and the normal component of magnetic flux density both are becoming what? Both are becoming zero exactly at the perfect conducting interface. So whereas the normal component of electric flux density and the tangential component of magnetic field intensity are not becoming equivalent to zero. Right. So dN1 is nothing but the maximum value of the electric flux density at the perfect conducting interface. Yes or no? Okay. See, previously dN2 is also present. So if you do dN1 minus dN2, if dN2 is also present, the overall value is going to decrease. Okay. Now here dN2 is becoming 0. So no field you are getting, no field is getting subtracted. So dN2 is becoming equal to 0. So dN1 will become equivalent to what? Rho s. So this is the maximum value of the normal component of electric flux density at the perfect conducting interface, right? Okay, so I can say this is the maximum value. So dN1 is maximum at what? At a perfect conducting interface. So what is that maximum value? Is equivalent to rho s. So if dN1 is maximum, I can write here from this equation, I can write En1 is equivalent to what? En1 is equivalent to rho s by epsilon 1. Can I write in this manner? Because dN1 is nothing but epsilon 1 into En1. So En1 is equivalent to rho s by epsilon 1. So En1 is also what? En1 is maximum at what? At a perfect conducting interface. At a perfect conducting interface. Okay, that's what I can conclude, right? Okay. Next, if you observe here, Bn1 and Et1 here, Bn1 and Et1, they are becoming 0 exactly at the perfect conducting interface. So which means I can say this normal component of magnetic flux density and the tangential component of electric field intensity are minimum or 0 at the perfect conducting interface. Okay, so I can say R minimum are 0 at what? At perfect conducting interface. They are becoming 0 or minimum at the perfect conducting interface. And here you are having what? You are having previously you are having HT1 difference HT2. Okay, now HT2 has become equal to 0. So that means HT1 is having its maximum value at the perfect conducting interface. See, whenever you are writing the boundary conditions, you have to keep in mind that you are writing those conditions exactly at the interface. So what actually happening exactly at the interface? So that's what you have to keep in mind, right? Okay. Okay. So Bn1 is equal to 0, Et1 is equal to 0. That means these normal and tangential components are becoming minimum or 0 at the perfect conducting interface. So this tangential component is equal to what? Js. So which means this tangential component is what? This tangential component is maximum at the perfect conducting interface. So here is maximum at a perfect conducting interface. So which means I can make some conclusion here. So that is the tangential component of electric field, right, and normal component of magnetic field. So here one more thing, here Bn1 means what here? Bn1 means I can write the same thing as what? As mu1 into what? Hn1 is equivalent to 0. So from here what I can get? I can write Hn1 is equivalent to 0. So that means normal component of magnetic field intensity is also becoming equivalent to what? 0 at the perfect conducting interface. So I can write E tangential and H normal here. E tangential and H normal components are becoming what? Are becoming 0 or minimum at what? At a perfect conducting interface. Right? Okay, this is the conclusion we can make. And one more conclusion we can make. So that is E normal and H tangential. E normal and H tangential components are becoming what? Are becoming maximum at what? At a perfect conducting interface. Right? Okay, so the tangential component and normal component, tangential component of electric field and normal component of magnetic field are becoming minimum or zero at the perfect conducting interface, whereas the normal component of electric field and tangential component of magnetic field must be maximum at the perfect conducting interface. I hope you know what do you mean by this tangential, how we are defining this tangential components and normal components. I hope you know that thing. Right, how we are defining the tangential and normal here? See, this tangential and normal are defined with respect to the interface here. See, for example here we have considered here z equal to 0. Here we have considered this z is equal to 0 as the interface, right? So z is equal to 0 is the interface, means this represents what? This represents xy plane. Right. So which means I can say that x and y components are acting like what? Tangential components. So the components that are parallel to this plane are called as what here? Tangential components. So since it is xy plane, x and y components are going to be parallel to this surface. So hence we call these components as what here? Tangential components. Tangential means those components are parallel to the interface. Right. Okay. So what is the component that is normal to the interface here? That is z component. So z component is the normal to the interface. So this is how you have to write the tangential component and normal component of fields. Right. Okay. Okay. Yeah. So this is with respect to what? Z equal to 0 interface. So if I change the interface, if I take y equal to 0 as the interface, y equal to 0 means it represents what? Zx plane. In that case, z and x components will behave as tangential and y component is going to behave as normal. Right? So in that manner, you have to understand the tangential components and normal components. So these are defined, tangential and normal components are defined with respect to the given interface, Okay. So coming to our rectangular waveguides here, you are having 4 conducting plates, 4 perfect conducting interfaces at what? At x equal to 0 and at x equal to a. At x equal to 0 and x equal to a. So this represents what? This represents a yz plane. That is placed at x equal to 0 and x equal to a. So here, what are the tangential components here? Tangential components are nothing but what? Are nothing but y and z components. Y and z components are nothing but tangential components. And what are the normal components here? Normal components are nothing but x component here. So with respect to this x equal to 0 and x equal to a perfect conducting interfaces, okay, the tangential components are nothing but what? Y and z components, and normal components is nothing but x component. Similarly, you have placed another 2 perfect conducting interfaces at what? Y equal to 0 and y equal to b. So at y equal to 0 and at y equal to b, you have placed another 2 perfect conducting interfaces. So y equal to constant plane means this represents what? This represents zx plane here. This represents zx planes. Right. Okay. So now see here, in this zx planes, what are the tangential components here with respect to this zx planes? What are the tangential components? Z and x components. So tangential components are nothing but what? Are nothing but z and x components. Right. And what is the normal component? Y component. So normal component with respect to this plates is nothing but what? Is nothing but y component. Right. Okay. So these things you have to keep in mind here. Right. So z and x components are called as tangential and y component is called as normal with respect to these 2 conducting plates. Right. And with respect to these 2 conducting plates, tangential components are y and z and normal components are x. Right. Okay. And one more thing, if you observe here, so if you observe here, if you observe the z component here, that is along the net propagation direction. Okay. So the z component with respect to these 2 conducting plates is acting like tangential. So similarly here also you are having z component. So this z component is also behaving as what? Tangential with respect to what? Zx planes. See, in both yz plane and zx plane, what is common here? Z is common. Understood? Okay, so that means z component with respect to these 4 plates here, with respect to these 4 plates, okay, this z component is behaving as tangential component, right? Whether it may be electric field or magnetic field. So if you consider Ez and Hz, okay, so these components are behaving like what? These components are behaving like tangential, either with respect to this yz planes or with respect to this zx planes also. It is behaving as what? These components are behaving as tangential components, right? Okay, okay, yeah. So these things are very, very important here. Right? Okay. Right. So I will tell you a trick how to write the field patterns inside the waveguide. So the field patterns inside the waveguide here. Field patterns inside the waveguide. How you can write? So whatever may be the field, inside the waveguide, how you can represent that pattern? Okay, so we know that we are having a rectangular waveguide here. I am considering a rectangular waveguide. This is the cross section of the waveguide. So this is A, broader dimension, and this is B, shorter dimension. So here you are having these 4 conducting plates like this, right? Okay, okay, yeah. So what I have told here, between any two conducting plates, you are going to have one standing wave pattern, and between these two you are having another 2 conducting plates, between bottom and top. So between bottom and top you must have what? You must have another standing wave pattern, okay, and along the plates you must have what? You must have the traveling wave pattern. So the traveling wave pattern will be along what? Will be along z direction. So this is z direction, right? And I am considering this as x and I am considering this as y. So this as y direction, right? Okay, x, y and z. So you must have the standing wave pattern between any 2 conducting plates. So one is the standing wave pattern between what? Between bottom plate and top plate. So as you move from bottom to top, what is going to vary? Y is going to vary. So that means you must have the standing wave pattern along what? Along y, right? And similarly here you are having 2 conducting plates at x equal to 0 and at x equal to a. So between, as you move between these 2 conducting plates, you are going to move along what? X direction. So which means you must have the standing wave pattern along what? Along x, right? Okay, so you must have a standing wave pattern along what? Along x here, along x, right? So you are going to encounter a standing wave pattern along x, and you are going to encounter standing wave pattern along y, and you must have the traveling wave pattern along what? Along z direction, that is along net propagation direction, right? Okay, okay. So the field patterns inside the waveguide, how we can represent here? So it is going to have, it must have the standing wave pattern. Along what? Along x direction, right? And this multiplied by, it must have standing wave pattern along what? Along y direction. Okay, so as you move along x, you are moving between the 2 conducting plates, that is x equal to 0 and x equal to a. So as you move along y, you are moving between another 2 conducting plates that is placed at y equal to 0 and y equal to b. So between any 2 conducting plates you must have standing wave pattern. So between x equal to 0 and x equal to a, you must have the standing wave pattern, and between y equal to 0 and y equal to b, you must have the standing wave pattern, and you must have the traveling wave pattern. Traveling wave pattern along what? Along z. Okay, so traveling wave pattern along z. So this whole thing multiplied by what? Multiplied by some constant. Okay, so you may have some constant value here. So Okay, so you may have here some constant here, some constant. So we don't know this constant value, there is no need to determine this constant also. Okay, okay. So the field patterns inside the waveguide is going to follow this pattern here. So that is the field patterns inside the waveguide can be represented as what? Some constant multiplied by standing wave pattern along x and standing wave pattern along y and traveling wave pattern along z, right? Okay, okay. So how we can represent the standing wave pattern along x here? So the standing wave pattern along x we can represent either in terms of what? Either in terms of sine function, or we can represent in terms of what? In terms of cos function. You can represent either in terms of sine function or cos function. So similarly, the standing wave pattern along y can also be represented either in terms of what? Sine function or what? Or cos function, or cos function, right? Okay, and the traveling wave pattern, we know how to represent the traveling wave pattern here. So this traveling wave pattern is represented as what? Is represented as e power j of omega t, or I can represent simply e power minus gamma z into e power j omega t. Okay, where gamma is equal to alpha plus j beta. So since we are treating the waveguide, as lossless, so hence alpha will be equal to 0. In place of gamma, you can replace what? J beta. Okay, so if you replace j beta, and if you simplify this, you can write it as what? You can write it as e power j of what? J of omega t minus what? Minus, you have to write here the change in phase along what? Z, right? Okay, okay. So here whenever you are representing the standing wave pattern, so here you have to write what? Phase, yes or no? So this is along what? This is along x. So you have to write here change in phase along what? Along x. So how you can write the change in phase along x here? The change in phase along x is nothing but what? Is nothing but the phase constant along x. So that I am representing with beta suffix x. Okay, so beta x into what? Into x. So this represents the change in phase along x. Next, cos of what? You have to represent here the change in phase along x. So that is beta x into what? X. Right, where beta x is the phase constant along what? Along x direction, right? Next, standing wave pattern along y. So here sine of what? Change in phase along y. So how you can write the change in phase along y here? So we know that phase constant represents what? Change in phase per meter. Now here I am defining that change in phase per meter along y direction. So along y direction, the change in phase per meter is represented by what? Beta y, right? If I want the change in phase over y meters, then how I can represent that phase is nothing but what? Beta y into y. So similarly, the phase along y here I can represent as what? Beta y into y. And here I have told that you are representing the traveling wave pattern along z. So here you have represented the change in phase with respect to time, and here you have to represent the change in phase along the net propagation direction, that is along z. Okay, so along z, what is the phase constant here? That is beta z, right? So here you have to represent beta suffix z here, beta suffix z. So beta suffix z represents the phase constant along the net propagation direction. So this beta z multiplied by what? Multiplied by z is going to give you the change in phase along the net propagation direction, right? Okay, so this is how you have to represent the field pattern inside the rectangular waveguide. So you are going to have some constant multiplied by some standing wave pattern. The solutions of those standing wave patterns are sinusoidal in nature, so it may be either sine function or it may be cos function. Since this is the standing wave pattern along x, here you have to represent the change in phase along x. The change in phase along x is given by what? Beta x into x. Okay, so in this manner you can easily remember here. So similarly you can write the standing wave pattern along y, right? So this multiplied by the traveling wave pattern along z. So in this manner you can represent the traveling wave pattern. So we know how to represent the traveling wave pattern, yes or no? So you can represent in this manner, right? Okay, so here in general this constant may be complex in nature. In general this constant may be complex in nature. right? So that means this overall field pattern, the solution whatever we have written here, so it is going to be what? It is going to be in complex in nature. So if you want, you can write a real time also. So if you take the real part of this complex solution, you are going to get what? Real time solution. Understood? Okay, so you can write the solutions of the field patterns inside the waveguide either in complex form, or you can write it in terms of what? Real time form. But in order to write the real time form, you have to know this constant value here. Okay, so if you know this constant value, then only you can write the real part, and you can write the real part of this complex quantity. Okay, otherwise it is not possible. So generally it is not that much needed to do all the calculations and simplifications to determine this constant value. It is not at all needed here. If you know this one, then it is more than enough, right? Okay, okay. So generally we will represent the field patterns in complex form itself, because in a real time solution, if you want, you have to do all the derivations and you have to determine this constant value. Okay, so which is not needed as far as GATE is concerned. Understood? Okay, okay. So here they are not going to ask you to derive this one complex solution or real time solution like that. So they are going to ask you based on what? Concepts, whether you have understood the concept clearly or not. That is what matters, right? Okay, okay. So this is how you are going to have, right? Now see here. So I am copying this field pattern here, right? Okay. Okay, right? Okay. So now see here. Now for example, if I want to write the tangential component of electric field here, suppose if I consider the tangential component of electric field, okay, let us assume I want to write the field pattern of this one, right? So I am saying that this electric field is what? Tangential component. So tangential component, how we are going to define, you know. Okay, we are going to define it with respect to what? Conducting plates. So if I want to write this field pattern, the tangential component of electric field pattern, okay, so let us assume if I want to write this one, right? Okay, so then how I can write here? See, for example, we know that here I have told that the Z component of electric field. So here I have told that Ez and Hz here, Ez and Hz are going to behave as what? Tangential component with respect to YZ planes, and also with respect to what? ZX planes. They are going to behave as what? Tangential component. Now suppose if I want to write a Z component of electric field, if I want to write the Z component of electric field here, Z component of electric field, if I want to write, how I can write here? So you have to follow this pattern, right? So we know that Ez is acting like what? It is going to act like a tangential with respect to what? With respect to ZX planes, right? It is going to act like tangential component with respect to YZ planes, and with respect to what? And with respect to ZX planes also. So you are having the YZ planes at x equal to 0 and at x equal to a. You are having the ZX planes at y equal to 0 and at y equal to b, right? Okay, okay. Yeah. So now see here, Ez is equivalent to some constant. Ez is equivalent to some constant. Okay, it is generally complex in nature. So this multiplied by standing wave pattern along x here. So you have to write the standing wave pattern along x, right? So that means if you move along x, what are the conducting plates you are going to encounter? That is x equal to 0 and x equal to a. So with respect to x equal to 0 and x equal to a, okay, what are the planes you are having? YZ planes. So that means with respect to this plates here, this Z component of electric field is going to behave as what? Tangential component. Yes or no? And we know that the tangential component of electric field must be what? Must be the tangential component of electric field must be what? Must be 0 at the perfect conducting interface. Okay, so that means this tangential component of electric field must be 0 at the perfect conducting interface. Here we are having, as you move along x, at what locations you are having perfect conducting interfaces? You are having at x equal to 0 and another one at x equal to a. So which means at x equal to 0 and x equal to a, the tangential component of electric field must be equivalent to what? Must be equivalent to 0. Yes or no? Now here this Ez, this Ez is acting like tangential component with respect to x equal to 0 and x equal to a plates. So at this perfect conducting interfaces, this Ez component must be equal to what? Must be equal to 0. Right? Okay. So if it has to become 0 here, so observe only standing wave pattern along x here. Okay. So standing wave pattern along x can take either, it may be either a sine function or it may be what? Cos function. Understood? But you have to choose either sine function or cos function here. So which one you have to choose? Such that this field component, that is the tangential component of electric field, has to become 0 at x equal to 0 and x equal to a. Okay, whenever you put x equal to 0 here, this function has to become what? Has to become 0. This field has to become 0. Okay, so at x equal to 0 here, at x equal to 0, it must become 0 means what you have to consider? Either sine function or cos function. If you put x equal to 0 here, so this term is becoming 0. Understood? So that means the standing wave pattern must be what? Must be sine function along x. Okay, so Ez, you can write it as what? You can write it as sine of what? Sine of beta x into what? Beta x into x. Right? Okay? Okay. So now if you put at x equal to 0, this tangential component of electric field will become equal to 0. And also at x equal to a also, this function has to become what? This function has to become 0. Understood? So this function has to become 0 at x equal to a means this sine function has to become 0 at x equal to a also. So that means at x equal to a, so this function will become what here? This function will become sine of what? Sine of beta x into a. So this must be equal to 0. This must be equal to 0. So when this function will become equal to 0? Whenever beta x into a is equivalent to what? Is equivalent to integral multiples of pi. Okay, so beta x a is equivalent to m pi. So therefore beta x is equivalent to what? I can write it as m pi by what? M pi by a. M pi by a. That's it. Right? So this beta x. So from boundary conditions, we have determined this beta x value. So that is nothing but m pi by what? M pi by a. That's it. Right? Okay. Next, similarly, if we try to write the standing wave pattern along y here. Okay. So along y. So that means if you are moving along y, you are going to encounter which conducting plates here? You are going to encounter zx plates, right? You are going to encounter zx planes. So this z component of electric field with respect to this zx planes is going to behave as what? Tangential component. So with respect to y equal to 0 and y equal to b, this Ez component is going to behave as a tangential component. So hence this tangential component of electric field must be 0 at y equal to 0 and at y equal to b. Okay, first let us consider at y equal to 0. So at y equal to 0, Ez must be equal to 0. So when, now consider only standing wave pattern along y here. So now at y equal to 0, this standing wave pattern, that means the field Ez has to become equivalent to 0. Okay, at y equal to 0, this Ez must be equivalent to 0. So which means you have to choose a sine function or cos function here, which is going to give you that result. If you put y equal to 0, sine function is going to give you 0, whereas this function is not going to give you 0. Understood? But here, according to our boundary conditions, at y equal to 0, Ez is the tangential component with respect to y equal to 0 plate. So the tangential component of electric field must be 0. Yes or no? Which means it must be what? Sine function. So the standing wave pattern along y must also be what? Must also be sine function here. Okay, so it is sine function. So sine of what? Beta y into what? Beta y into y. Right? Okay, so similarly, similarly here Similarly here, if you apply the boundary conditions with respect to what? With respect to this y equal to b here. So at y equal to b, at y equal to 0, this field is becoming 0. At y equal to b also, this field has to become 0. So at y equal to b, what you are going to get? Sine of beta y into what? Into b must be equal to 0. So that means beta y into b must be integral multiples of pi. So now that integer I am representing with n here. Since here I am representing the integer with m, so here I am going to represent the integer with respect to n. Okay, so here beta y is equivalent to what? N pi by what? N pi by b. Beta y is equivalent to n pi by b. Right? Okay. Okay. So just replace here beta y with what? N pi by what? N pi by b. N pi by b, right? Okay, so this multiplied by e power j of what? This multiplied by e power j of omega t minus what? Minus beta z into what? Beta z into z. So this is how you can write the expression for the Ez in case of what? Rectangular waveguide, right? Okay, so the z component is going to behave as tangential with respect to what? With respect to 4 conducting plates. Okay, if you apply the boundary conditions at those 4 conducting plates, you are going to get the standing wave patterns in this manner, right? Okay, okay. So now if you want, you can check here beta x is m pi by a. Now at x equal to 0, this has to become 0. Yes or no? At x equal to a also, it is going to become 0. Next, at y equal to 0 also, it will become 0. At y equal to b also, this function will become equal to 0. So at each and every perfect conducting interface, it is satisfying the boundary conditions. It must satisfy the boundary conditions, right? Okay. So based on the boundary conditions only, we can write the solutions. We can write the solutions of the field patterns inside the rectangular waveguide. Okay, so there is no need to do all the mathematical calculations and derivations and all those things in order to write these solutions here. So you can just write with the help of what? Boundary conditions in this manner. Okay, so now similarly, if you want to write for a hz here, if you want to write for hz, okay, so hz is also act like what? It is also going to act like a tangential with respect to what? With respect to x equal to 0 and x equal to a plates, and also with respect to what? With respect to y equal to 0 and y equal to b plates. So that means along x, if you move along x, so this z component is acting like what? Tangential component. So because you are having the perfect conducting interfaces at x equal to 0 and at x equal to a. X equal to 0 and x equal to a. So they are nothing but yz planes. So with respect to yz planes, this z component is going to behave as tangential component, and you are having two more conducting plates at bottom and top. Okay, with respect to these 2 conducting plates, the z component is going to act like what? Tangential. So with respect to 4 conducting plates, this is going to act like tangential component only, right? And we know from the boundary conditions here, from the boundary conditions, we know that the tangential component of magnetic field, the tangential component of magnetic field must be what? Must be maximum at the perfect conducting interface. Must be maximum at perfect conducting interface means it should not be 0 here. It should not be 0 at the perfect conducting interface. Okay, it is non-zero at the perfect conducting interface, right? Okay. Right. Okay. So now see here. So hz is going to act like tangential with respect to x equal to 0 and x equal to a, and y equal to 0 and y equal to b. So we know that h tangential must be maximum here, must be maximum at a perfect conducting interface, at perfect conducting interface. Okay, so hz is equal to what? You have to write some constant multiplied by standing wave pattern along x. Okay, so at x equal to 0 and at x equal to a and y equal to 0 and y equal to b, this field is going to behave like tangential, and tangential component of magnetic field must be what? Must be maximum at the perfect conducting interface. So if it must be maximum means here the standing wave pattern you have to choose either sine function or cos function here. At x equal to 0, this standing wave pattern must have what? Its maximum value. Yes or no? It must be maximum at x equal to 0. So which means you have to consider sine function or cos function. You have to consider cos function, right? Okay. So similarly here, so here you have to consider cos function. Hz is equivalent to. So since this tangential component of magnetic field must be maximum, we have to write the standing wave pattern as what? Cos of beta x into x, where beta x we have already determined. Beta x is m pi by a and beta y is n pi by b. So cos of what? Cos of m pi by a into x, right? Next, similarly here, if you consider with respect to what? Y equal to 0 and y equal to b plates. So that is nothing but zx planes here. So with respect to zx plates also, this hz is going to behave like what? Tangential component. So this tangential component of magnetic field must be what? Must be maximum at y equal to 0 and y equal to b plates also. Yes or no? So if it is maximum means what is the standing wave pattern you have to get? You have to get sine function or cos function? You have to get cos function. Okay, so you can remember this easily in this manner, that is whenever at the perfect conducting interface if the field component is becoming 0 means, okay, the standing wave pattern must be sine function. If it is becoming maximum means the standing wave pattern must be cos function. You can remember in this manner in a simple way, right? So cos of m pi by a into x and here this multiplied by cos of what? Cos of n pi by b into y. So this multiplied by what? This multiplied by traveling wave pattern along z. So that is e power j of omega t minus beta z into what? Into z. Okay. So remember that this m pi by a is nothing but what? Is nothing but beta x and this n pi by b is nothing but what? Is nothing but beta y. Right? Okay. Okay. Right. So with the help of this boundary conditions we have written the z component of electric field and the z component of magnetic field, right? So what is the z component of electric field? We got some constant multiplied by what? Multiplied by sine of m pi by a into x multiplied by sine of what? N pi by b into y into what? E power j of omega t minus beta z into what? Z. Okay, hz is equal to what? What we got? Some constant multiplied by what? Multiplied by cos of what? Cos of m pi by a into x into cos of what? Cos of n pi by b into y into what? E power j of omega t minus beta z into z. Okay. Okay. So these are the solutions for Ez and Hz here. Ez and Hz. Right? Okay. Okay. So now we have written these solutions just with the help of what? Just with the help of boundary conditions. Boundary conditions. Right? Okay. So I hope this is crystal clear here. So where m pi by a is equivalent to what? Beta x and n pi by b is equivalent to beta y. Okay. So here I am defining one more parameter, so that is h square here, h square. So I am representing this h square as m pi by a whole square plus what? Plus n pi by b whole square. So just remember this one here. Okay. So I am not going to derive all these things, but just you can remember this. So that is h is equal to, I can represent it as square root of what? Square root of m pi by a whole square plus what? N pi by b whole square. Or in simple terms you can represent h is equivalent to what? Square root of what? Square root of beta x square plus what? Beta y square. Right? Okay, I have defined one more parameter, that is h, which is equivalent to square root of m pi by a whole square plus n pi by b whole square, right? So that is beta x square plus beta y square, right? Okay. Okay. So now see here. See, in rectangular waveguides, with the help of what? With the help of Maxwell's equations. With the help of Maxwell's equations, we can get the relation between what? Between the transverse field components and longitudinal field components. So what do you mean by this transverse field components and longitudinal field components? See, if the field components that are perpendicular to net propagation direction, we call them as what here? We call them as transverse field components. So the components that are along the net propagation direction, we call them as longitudinal field components. So if you consider the rectangular waveguide here, if you consider the rectangular waveguide, okay, so here the traveling wave pattern is along what? Z direction, and the plane that is perpendicular to this net propagation direction is nothing but what? XY plane, right? Okay, so which means x and y components are the components that are normal to what? That are normal to net propagation direction. Okay, so the components that are normal or perpendicular to net propagation direction, we call them as what? Transverse field components. Okay, and the components that are along the net propagation direction, we call them as what here? We call them as longitudinal field components. So which means in case of rectangular waveguides here, the transverse field components are nothing but what? Are nothing but Ex, Ey, Hx and Hy. So these are called as what? These are called as transverse field components. So these are the components that are perpendicular to what? That are perpendicular to net propagation direction. So these are perpendicular to net propagation direction. Okay, next the components that are along the net propagation direction are nothing but what? Ez and what? Ez and Hz. Okay, so these field components, we call them as what here? We call them as longitudinal field components. We call them as longitudinal field components, right? Okay, so these are the components that are what? That are along what? That are along net propagation direction. Along net propagation direction. So these are called as longitudinal field components, and these are called as transverse field components. So with the help of Maxwell's equations here, right? With the help of Maxwell's equations, we can relate this transverse field components and longitudinal field components. So we are not going into those derivations and all. So here just I am going to give you the relation between the relation between the transverse field components and longitudinal field components. Okay, we can represent all the transverse field components in terms of what? Longitudinal field components. So how we can represent? I will give those equations. Okay, see here, this is Ex, right? Ey, Hx, Hy. So we can express all these transverse field components in terms of what? In terms of longitudinal field components. So how we can represent? See here. So Ex is equivalent to, so here you have to write minus j omega mu by h square. So here j omega mu by h square. I have told what is h. Okay, and here you have to write j omega epsilon by h square, and here you are going to get minus j omega epsilon by h square, right? Next here you are going to get one term here. You are going to get one differentiation here. Okay, I will explain what is that, right? And next here you are going to have minus sign, and here you are going to get j beta z. So beta z is the propagation constant along the net propagation direction, sorry, phase constant along the net propagation direction. So j beta z by h square. So in each and every term, in each and every expression, Okay, the second term will be what? The second term will be j beta z by h square only. Okay, so everywhere this is second term, this is the first term and this is the second term. So in the second term everywhere you must have what? Minus j beta z by what? H square. So here also you must have minus j beta z by h square, right? Okay, okay. So here you are going to have one differentiation here, right? Okay. So ex, ey, hx, hy. So the first term must have, ex must have minus j omega mu by h square term, and the second term is minus j beta z by h square term. Okay. So similarly for ey, similarly for hx, similarly for hy, I have written. Okay. So here I said that we are writing this transverse field components in terms of what? Longitudinal field components. So what are the longitudinal field components? Ez and hz. So here in the first term, whenever you are writing for ex, so here differentiate the z component of magnetic field here, the z component of magnetic field with respect to what? With respect to y. Okay, so whenever you are writing for ex, here differentiate the z component of magnetic field with respect to what? With respect to y. Next, in the second term, differentiate the z component of electric field. So this is electric field, here this is also electric field. So whenever you are differentiating the electric field, differentiate it with respect to what? Here you are having x, so here you differentiate it with respect to x. So if you are differentiating z component, differentiate with respect to y. If you are differentiating the z component of electric field, differentiate it with respect to x. Okay, so in the same manner, you can write for the expression for ey. So here you have to differentiate, in the first term you have to differentiate the z component of magnetic field with respect to what? With respect to x. Okay, so that is dou hz by dou x. In the second term you have to differentiate the z component of electric field with respect to what? With respect to y only. So that is dou ez by what? Dou ez by dou y. Right. So you have written for ex and ey. Next you are writing for hx here. You are writing for hx. So how you can write for hx here? So here differentiate the z component of electric field. Now differentiate the z component of electric field with respect to what? With respect to y. So that is dou ez by dou y. Next here differentiate the z component of magnetic field with respect to what? With respect to x only. Okay, so that is dou hz by what? Dou hz by dou x, right? And here differentiate the z component of electric field with respect to what? With respect to x, with respect to x. And here differentiate the z component of magnetic field with respect to what? With respect to y. Okay, so in this manner you can easily remember the relations between what? Relations between the transverse field components and what? And longitudinal field components. So this is the relations between the transverse field components and longitudinal field components. Okay, okay. So these are the relation between what? Between transverse and longitudinal field components, right? Okay, okay. So this is how we can represent the relation between the transverse field components and longitudinal field components. See, from this we can observe one thing here, right? So that is see here, what is the main observation that we can do here is if suppose the longitudinal field components becomes 0 here. Let us assume Ez is equal to 0. If let us say Ez is equivalent to 0 and Hz is equivalent to 0 here. If Ez equal to 0, Hz equal to 0. So if you put Ez equal to 0, Hz equal to 0 in all these expressions, all these field components will also become equal to 0 or not. So if Ez equal to 0 and Hz equal to 0, this implies Ex, Ey, Hx and Hy, all these field components will also become what? Will also become equivalent to 0. Yes or no? So which means no field components are going to present inside the waveguide if both the longitudinal field components will become equivalent to 0. Okay, okay, yeah. So which means this condition is not at all possible inside the rectangular waveguide. So if both Ez and Hz becomes 0, no field components can propagate inside the waveguide, right? So which means this is not possible inside the waveguide. This is not possible. This condition is not possible inside the waveguide. So if it happens, then all the field components will become equivalent to 0. There will be no fields that are going to present inside the waveguide, which means there will be no wave propagation inside the waveguide, right? So this is not at all possible here. Now here I will tell you one thing, that is the conditions for TE mode, the conditions for TE mode, and the condition for TM mode, and the condition for TEM mode, TEM mode. So the condition for TE mode, the condition for TE mode is Ez. So if there exists no electric field component along the net propagation direction, then we call it as what here? TE mode. So Ez is equal to 0 and Hz is not equal to what? Hz is not equal to 0. There exists no electric field component along the net propagation direction, but there exists a magnetic field component along the net propagation direction. Then we call that mode as what here? We call that mode as a TE mode. Okay, if there exists no magnetic field component, if there exists no magnetic field component along the net propagation direction, okay, so that is Hz is equivalent to 0 and Ez not equivalent to 0, then that mode we call it as what here? We call it as TM mode, right? Okay, so next TEM. TEM means if there exists no component of electric field as well as magnetic field along the net propagation direction. So that is the condition for TEM is both Ez equal to 0 and what? And Hz is equal to 0. So I am talking about waveguides here, right? Okay, so in rectangular waveguide, right? Okay, so this is how we are going to define TE, TM and TEM, right? Okay. Okay, what is the condition for TE here? So Ez must be equal to 0, whereas Hz is not equal to 0. That is, along the net propagation direction, the electric field component must be 0, whereas the magnetic field component not equal to 0. That is the condition for TE mode. What is the condition for TM mode? If there exists no magnetic field component along the net propagation direction, but there exists a electric field component along the net propagation direction, then that mode is called as what? TM mode. So if both Ez equal to 0 and Hz equal to 0, that mode we call it as what? TEM mode, right? Okay, that mode we can call it as a TEM mode here, right? Okay, so now here in general we are going to represent the subscript for TE. So the subscript for TE we generally represent MN here, MN. So M is an integer, N is also an integer. So here M represents the number of half cycles, of the standing wave pattern, along x direction, okay, whereas N represents what? N represents number of half cycles of the standing wave pattern along what? Along y direction. We know that we are going to have the standing wave patterns along what? X direction as well as what? Y direction. So M represents the number of half cycles here, the number of half cycles of that standing wave pattern. Okay, okay, and N represents the number of half cycles of the standing wave pattern along y direction, whereas M represents along what? Along x direction, right? Okay, okay. So here also for TM also we can have what? You can have different types of modes depending upon M and N values. So whereas in case of TEM, okay, so TEM itself is called as a mode, right? So it is a separate mode here, so which is called as TEM mode. We generally call it as TEM mode. So here you are not going to have any standing wave patterns and all those things, right? Okay, okay. So that's why we don't have the subscript like M and N like that, right? Okay. So these are the conditions for TE mode and TM mode and TEM mode. Now if you observe here, okay, so if Ez equal to 0 and Hz equal to 0, all the field components are becoming equal to 0. So this is the condition for what? Ez equal to 0 and Hz equal to 0 is the condition for what? TEM mode. So whenever it is becoming 0, all the other field components are also becoming 0, which means TEM mode is not at all possible in case of what? Rectangular waveguides. So that is the conclusion we can make here. So what is the conclusion we can make? TEM mode is not possible, is not possible in case of what? Is not possible in rectangular waveguides, okay. So TEM mode is not possible in case of what? In case of rectangular waveguides. So that is the conclusion we can make, right? Okay, so what are the modes that are possible here? TE mode may be possible and TM modes are also possible, right? Okay, so for TE mode what will happen? Ez will become equal to 0. That means this term will be 0, this term will exist. This term will be 0, this term will exist. This term will be 0, this term will exist. So this term will be 0, this term will exist. So overall all the field components are going to exist, right? Okay, whereas for a TM mode, so for TM mode, what must be 0? Hz is equal to 0. So if you put Hz equal to 0, this first term will be 0, this second term exist. And here Hz equal to 0, first term will become 0, second term will exist. Here this second term will become 0, first term will exist. Here second term will be 0, the first term will exist. Yes or no? Okay, so that means TE modes are possible and TM modes are also possible, whereas TEM mode is not possible in case of what? In case of rectangular waveguides, right? So that is the conclusion we can make here, right? Okay. So one more thing here. So if I consider TE mode, TEMN, right? So Ez is equal to 0 and Hz is not equal to 0. So we have already get the solution. For Hz. Yes or no? Already we have determined or not? Hz. How this Hz component is going to look like inside the waveguide? How it is going to look like? I have already told you. So Hz is nothing but what? It will look like some constant multiplied by cos of m pi by ax into cos of n pi by b into y into e power j of this term. Okay, so that's how the Hz is going to look like, right? Okay, so here Ez is 0, right? But whereas Hz is not equal to 0, so here Hz is equivalent to what? Hz is equivalent to, you are going to have some constant. So Hz must be maximum at x equal to 0 and at x equal to a. So if it is maximum means the standing wave pattern must be cos function, that is cos of m pi by a into x, right? So similarly it must be maximum at y equal to 0 and y equal to b plates. So that means it is maximum means it must be what? Cos function. So cos of what? Cos of n pi by b into y into what? E power j of omega t minus beta z into what? Into z, right? Okay, so if you know this Hz here, okay, you know this Hz, right? And if you place Ez equal to 0, and Hz equal to this one, right, then you can get all the expressions for what? For Ex, Ey, Hx and Hy. Yes or no? Here you can get the expressions for Ex, Ey, Hx and Hy. Yes or no? So here we are having the relation. Between the transverse field components and longitudinal field components. So here put Ez equal to 0 and Hz, substitute that solution. You are going to get the solution for Ex. Similarly, you can get the solution for Ey. Similarly, you can get the solution for Hx. Similarly, you can get the solution for Hy. So this will represent the solutions for what? TE mode, right? Okay, so you can write all the field components inside the rectangular waveguide with the help of these equations. Yes or no here? Okay. So now see here. Now we have to check which modes are possible. Now we have to check which modes are possible. So one thing we are clear that in TE mode already Ez is equal to 0. If Hz also becomes equal to 0, okay, then that modes are not at all possible inside the waveguide. Right? We know that one. Right? Okay. Okay. So now see here. Now see here for TE MN mode here, for TE MN mode. So for TE MN mode, if I write the expressions for EX, EY, HX, HY. Okay. So what you are going to get? So Ez equal to 0, Hz is not equal to 0. So you are going to have only second term, that is minus Z beta Z by H square into dou Hz by dou, you must have only first term here, not second term. Ex equal to J omega mu by H square minus J omega mu by H square into what? Into dou Hz by dou Y, right? Okay. So here you must have dou Hz by dou Y. So this is equivalent to what? Minus J omega mu by H square. So what is dou Hz by dou Y here? So differentiate this function with respect to Y. So if you differentiate this function with respect to Y, what you are going to get? You are going to get some constant here. So multiplied by n pi by b into cos of m pi by a into x into what? Sine. So you are going to get minus sign. So minus of minus will become plus. So sine of n pi by b into y into e power j of omega t minus beta z into z. Okay. Just I am doing the differentiation. That's it. Since you are doing the differentiation with respect to y, okay, the function with respect to x and the function with respect to z will become what? Will behave as constants with respect to y. So differentiate only the function of y term, right? Okay. Okay. So Ey is equal to what you are going to get? Minus j omega mu by h square into what? Dou hz by dou x. So this is equivalent to what? This is equivalent to, we have to differentiate the x term here. You have to differentiate only the term which is a function of only x. Okay. Okay. So what you are going to get? So here you are going to get, so this is not minus j here, this is plus j, right? Okay. So you are going to get here j omega mu by h square into constant. So multiplied by, I am differentiating now hz with respect to x. So m pi by a into what? Sine of m pi by a into x. Okay. So here you are going to get minus sign. Next, this multiplied by cos of n pi by b into y into e power j of what? Into, see, I am doing the analysis for TE mode. Okay. For TM mode you have to do in the same manner, right? Okay. Right. Next, for hx here, hx, what you are going to get? The first term will be 0, the second term you are going to have. So you are going to have minus j beta z by h square into what? Into dou hz by what? Dou hz by dou x, right? Okay. So this is equivalent to, you are going to get minus j beta z by h square. So if you differentiate hz with respect to x, you are going to get what? You are going to get the same term here. So that is multiplied by m pi by a into what? Sine of what? Sine of m pi by a into x into cos of n pi by b into y into e power j of omega t minus what? Minus beta z into z, right? Okay. Right. Next, similarly you can write for hy here. You can write for hy. So hy is equivalent to what? Is equivalent to minus j beta z by h square into what? Dou hz by dou y. Dou hz by dou y. So this is equivalent to, this is equivalent to what you are going to get. You are going to get a dou hz by dou y. Okay, so that is minus j beta z by h square, right? Okay, so differentiate hz with respect to y. So what you are going to get, some constant into n pi by b, n pi by b into what, cos of m pi by a into x multiplied by what, multiplied by sine of, so minus sign you are going to get minus of minus will become plus here. Okay, sine of n pi by b, n pi by b into y, right, n pi by b into y multiplied by e power j of omega t minus beta z into what, into z, right? So this is the expression for hyr, this is the expression for hy. Okay, okay, so we got all the expressions for what, for TE mode. Okay, and we are having a hz, right? Okay, so hz also I am writing here, hz is equal to what, some constant multiplied by what, cos of m pi by a into x multiplied by cos of n pi by b into y into e power j of omega t minus beta z into z. I have written all the field components of what, of TE mode here, of TE mode, right? So this is a TE m. So Ez is equivalent to 0 and Hz is not equal to 0. So for this mode I have written. Okay, okay. So now tell me from here which modes are possible, which modes are possible. Okay, so that means see, we know that m and n values will take all the integer values here. Okay, so by varying m and n, okay, we can judge which modes are possible. So m and n represents mode numbers here, m and n represents mode numbers. Okay, so they are nothing but m and n represents what, mode numbers, and they will represent what, they will represent the number of half cycles along x direction and along y direction respectively, right? Okay, okay, so now from here let us see which modes are possible and which modes are not possible. So let us consider which color we'll take here, we'll take a blue color. Okay, okay, so see here right? Okay, so let us take a TE M0 mode here. Let us take a first let us take a TE00 mode. So I am taking m equal to 0 and n equal to 0, right? So here I have considered m equal to 0 and n equal to 0. So let us check whether this mode is possible or not. How we can check here? Because here we have to replace m equal to 0 and n equal to 0 in these expressions here, right? Okay, so if you put m equal to 0 and n equal to 0, so let us take ex. Okay, here you are having n, so if you put n equal to 0, ex will become 0. Here you are having m, if you put m equal to 0, ey will also become 0. Here you are having m, so hx will also become 0. Here you are having n, so hy will also become 0. Here only hz component will be left out. Yes or no? If you put m equal to 0 and n equal to 0, okay, you are not going to have what? You are not going to have this function of x and you are not going to have this function of y, because if you put m equal to 0 and n equal to 0, this will become 1 and this will become 1. And if you observe, hz will become independent of what? X and y. So if hz becomes independent of x and y, if hz becomes independent of x and y, okay, and here we are differentiating. Here we are differentiating this hz component with respect to what? Wait, where it is? Okay, fine, no problem. So what I am saying here is okay, So all this Ex, Ey, Hx, Hy, all these field components will become what? Will become 0. So now, is there any chance for Hz only to exist here? So without these field components here, without Ex, Ey, Hx, Hy, and Ez is also equal to what? Ez is also equivalent to 0. Okay, so here if all these field components are becoming 0, is there any possibility for Hz to be to exist here? For Hz to exist, tell me. Is there any possibility only Hz to exist? No, because here we are dealing with what? Electromagnetic waves. So electromagnetic wave means what? You must have what? Both electric field as well as what? Magnetic field. So electric field components are producing the magnetic field components, and this magnetic field components has to produce the electric field components, vice versa. Yes or no? That is the property of a electromagnetic wave. Okay, if all the field components here becoming 0, there is no possibility for Hz only to exist. Only magnetic field component cannot exist. Yes or no? It is not at all possible. Right? Okay, since we have not derived here the constant term here, we have not derived the constant term here. Okay, so here it may be depend upon m and n values. So if it depends upon m and n values, then Hz will also become equal to 0 for m equal to 0 and n equal to 0. Even if we don't know this constant value, we can easily guess, or we can easily tell that only Hz component is not at all possible. Only one magnetic field component is not at all possible, because that doesn't represent an electromagnetic wave itself. Okay, so it is not at all possible. So if Ex equal to 0, Ey equal to 0, Hx equal to 0, Hy equal to 0, and Ez is also 0, okay, then in that case Hz must also become equivalent to 0. But mathematically, if you observe here, if you put m equal to 0, n equal to 0, this function is not becoming 0. But here you are having constant term here. So this constant term may depend upon m and n values. Since we have not derived that, we don't know, right? Okay, but we can guess that it may also depend upon m and n values. Why means mathematically also it has to satisfy. Right, if you put either if you put m equal to 0 and n equal to 0, this Hz must also become equivalent to what? Equivalent to 0. Right, okay, or if it is not mathematically, so theoretically also we can easily guess that Hz cannot exist, because only magnetic field component is not at all possible in case of electromagnetic wave. Okay, okay, so which means this TE00 mode is not at all what? Is not at all possible. TE00 mode is not at all possible. So this mode is not at all possible in case of rectangular waveguide, right? Okay, so next we will check for TE-M0 mode. TE-M0 mode. So that means here I am considering m not equal to 0 and n equal to 0. So let us check whether these modes are possible or not. Now here I am putting only n equal to 0 but m not equal to 0. Okay, if you put only n equal to 0 here, if you put only n equal to 0, so this Ex component will become 0, right? But Ey component will exist or not? Yes or no? M is not equivalent to 0. Right, only n equal to 0. If you put n equal to 0, this cos function will become 1. Okay, but overall this sine function will exist, e power z term will also exist. Yes or no? We are going to have one standing wave pattern and one traveling wave pattern in case of what? TE-M0 mode, right? Okay, okay. And if you observe Hx here, if you observe Hx, if you put n equal to 0 and m not equal to 0, so this term will also exist. Hx will also exist, whereas Hy will become what? If you put n equal to 0, this term will become what? This term will become 0, right? And in case of Hz, if you put n equal to 0, so here also you are having what? Cos function, right? So one standing wave pattern and one traveling wave pattern. So here Hy is becoming 0 and Ex is becoming 0, whereas Ey and Hx are existing and Hz is also existing. Okay, so you are having electric field component as well as what? Magnetic field components. If you observe here, the magnetic field components are present in what? Zx plane. Yes or no? So this is Z component, this is X component. So both are present in Zx plane. Okay, and Ey is present along Y direction. So Y is perpendicular to what? X and Z. Okay, so electric field and magnetic fields are mutually perpendicular to what? One another. So this y component is producing the magnetic field component in zx plane, which is going to have x and z components. So that is a possibility. Yes or no? So which means here in case of TE M0 mode, Ex is becoming 0, Hy is becoming 0, whereas Ey, Hx and Hz are present. Okay, so which means these modes are possible inside the waveguide here. So in TE M0 mode, what are the field components that are becoming 0? So Ex is becoming 0 and Hy is becoming 0. Right? What are the components that are existing? Ey is present, Hx is present, and Hz is also present. Right? Hz must be present here because already Ez equal to 0. Okay, Hz must be present. Right? So TE M0 mode is possible here. TE M0 mode is possible. This mode is possible. So that means what? TE 00 mode is not possible. TE 10 is possible, TE 20 is possible, TE 30 is possible, and so on. Right? Okay. So all those modes are possible. Right? Next, similarly, if you do the analysis with respect to what? With respect to TE 0n here. TE 0n. Here m equal to 0 and n not equal to what? N not equal to 0. M equal to 0 and n not equal to 0. So in this case, okay, what are the field components that are going to exist? See here. So m equal to 0 and n not equal to 0. If you put m equal to 0, right, then Ey component will become 0 and Hx component will also become 0, whereas Ex is not equal to 0 and Hy is not equal to 0 and Hz is also present. Okay, so for TE 0n mode, what are the components that are going to present here? So Ex will be present and Hy, Ex will be present and Hy will be present and Hz is also present, right? So whereas Ey will be 0 and Hx will be 0 and Ez is also what? Ez is also 0. So here also you can write Ez equal to what? 0, right? Okay, so this TE 0n mode is also what? It is also possible. It is also possible, right? For n not equal to 0, right? Which means TE 01 mode, TE 02 mode, TE 03 mode, and all those modes are possible, right? Okay, okay. Next, similarly, if you consider TE Mn here, if you consider TE Mn, where m is not equal to 0 and n not equal to 0. We know that if m equal to 0, n equal to 0, that mode is not at all possible. If m not equal to 0, n not equal to 0, then in that case, all these field components will exist or not? If m not equal to 0, n not equal to 0, then all these field components are going to exist. Okay, so except Ez, all the other field components is going to exist for TE Mn. So for this one, Ex is going to exist, Ey is going to exist, Hx is going to exist, Hy is going to exist, Hz is also going to exist. Only Ez will become equivalent to 0, right? Okay, okay. So all these modes are possible here. These modes are possible, right? So in case of TE mode, what is the conclusion we can take here? So TE Mn, so the condition is Ez equal to 0 and Hz not equal to 0. So in this case, what are the modes that are possible? TE00 mode is not at all possible, whereas TE M0 mode is possible. Here m not equivalent to 0 and n equivalent to 0, right? Similarly, TE0n mode is also possible. Here m equal to 0 and n not equal to 0. So similarly, TE Mn modes are also possible. Here m not equal to 0 and n not equal to 0, right? Okay, okay. So I hope these things are crystal clear here. I hope these things are crystal clear, right? Okay. Right. So we have seen how to check which modes are possible inside the rectangular waveguide, right? Okay, so these are the conclusions we can make, right? Okay, so now here I am taking break here. So at this point I am taking break for 10 minutes. I am taking here 10 minutes break I am taking, right? Okay, so we'll meet again at 12:10 p.m. here, again at 12:10 p.m. Okay, we'll meet at 12:10 p.m. So now it is almost 12 o'clock. Okay, so we'll meet at 12:10, right? Okay. So after break we'll continue this one here, right? So I hope each and everything is crystal clear, right? Okay. Okay, so we'll meet after 10 minutes. So hi everyone, so welcome back. So 10 minutes break is completed, right? Okay. 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 So see, nobody is watching here, right? Okay. So nobody is there in online. So what is the purpose of taking this live session here? Right? Okay. I think even if it is recorded also, that would be enough for you. I think live is not at all needed, right? Okay. Okay. If students are there, then we'll get the interest to teach in live also, right? If nobody is there, what is the purpose of teaching in live, right? Okay. Even we lose the interest to teach here, right? Okay. Okay. So we have seen what are the modes that is possible, that is in TE mode, right? So we have studied about this TE mode. So similarly we can do the same analysis with respect to TM mode here, right? So TM MN. So what is the condition? Hz is equivalent to 0, whereas Ez is not equivalent to 0. So we have already derived the expression for Ez here. We have already derived the expression for Ez. So what is the expression for Ez here? So Ez is equivalent to some constant. So multiplied by what? Multiplied by sine of m pi by a into x into sine of n pi by b into y into e power j of what? Omega t minus beta z into z, right? Okay. Okay. So here hz is already 0, right? And if Ez also becomes 0 here, if suppose Ez also becomes 0, okay, we know that in rectangular waveguide, if Ez equal to 0, Hz equal to 0, that mode is not at all possible. Yes or no? If Ez equal to 0, Hz also becoming equal to 0 means it represents TEM mode. And we know that in rectangular waveguide, this TEM mode is not at all possible, right? Okay. Okay. So here, so let us check which are the modes that are possible here. So let us take TM00 mode. Let us take TM00 mode. So if you put m equal to 0 and n equal to 0, this z component is becoming equal to 0. So already Hz equal to 0, now Ez also becoming 0. So if both Ez and Hz becomes 0, all the other field components Ex, Ey, Hx, Hy will also become equal to 0, which means no fields are going to exist inside the waveguide for m equal to 0 and n equal to 0 mode. So which means TM00 mode is not at all what? It is not at all possible, right? Okay. Now let us check TM-M0 mode here, TM-M0 mode. So here m is not equal to 0 and n is equivalent to what? N is equivalent to 0. Let us check whether this mode is possible or not. Okay. Now see here. If you put m not equal to 0, but if you put n equal to 0, so since it is sine function, if you put n equal to 0, this field will become equivalent to what? 0. So if Ez becomes 0, already Hz equal to 0. So if Ez and Hz becomes 0, all the other transverse field components will also become equal to 0. So this mode is not at all possible. So TM M0 mode is also what? Is also not at all possible. It is not at all possible. Next, similarly, if you consider TM0N mode, TM0N mode. TM0 n mode. So that is here m equal to 0 and n not equal to 0 and n not equal to 0. Okay, so here also if you put m equal to 0, the field component will become equal to what? 0. Yes or no? So if Ez becomes 0, already Hz equal to 0. So if Ez and Hz becomes 0, all the transverse field components will also become equal to 0. Okay, so that's why this mode is also what? This mode is also not at all possible, right? Next, if I consider Tm, if I consider Tm Mn mode, Tm Mn mode, where m is not equal to 0 and n is also not equal to 0. So if m not equal to 0 and n not equal to 0, if m not equal to 0, n not equal to 0, so then Ez will exist or not? M is not equal to 0 and n is not equal to 0. So then this standing wave pattern is possible, this standing wave pattern is also going to present. Okay, so then in that case Ez is going to be present. So if Ez is present, then the transverse field components are also going to present. Yes or no? Only Hz is becoming 0 but Ez is not equal to 0. In that case, what will happen? All the other field components Ex, Ey, Hx, Hy will also be present. Understood? Okay. Okay. So for m not equal to 0 and n not equal to 0, these modes are what? These modes are possible. These modes are possible. Okay. Okay. So that means TM11 mode is possible and TM12 mode and TM13, TM14 and so on up to TM1 13, 14, 15 and so on. So like this all the modes are possible, and similarly you can write TM21, TM22, TM23 and so on. All these modes are also possible, right? Okay, so that means all the modes here for which m not equal to 0 and n not equal to 0, all the modes are possible in case of what? TM mode. Right. So what are the modes that are not possible? TM00 mode is not possible, and TM-M0 mode is also not possible, and TM0N mode is also not possible, and TM-MN mode is possible where m not equal to 0 and n not equal to 0. Right. Okay. So if you compare TE-MN and TM-MN, so what are the modes that are possible here? So TE00 is not possible, TE-M0 is possible, here m not equal to 0, n equal to 0, and TE0N mode is also possible, here m equal to 0 and n not equal to 0. Next, TE-MN mode is also possible, here m not equal to 0 and n not equal to 0. Right. So whereas for TM case, TM00 mode is not possible, TM-M0 mode is also not possible, TM0N mode is also not possible, TM-MN mode is possible. Okay, so here m not equal to 0 and n not equal to 0. Only these modes are possible in case of what? TM. Right. Okay. Okay. Right. Okay. So this is how we can tell which modes are possible and which modes are not possible, right? Okay. So basically most of the questions in case of rectangular waveguides are going to based upon the cutoff frequency here. So I am not deriving that cutoff frequency and all, right? Okay, so I will just give you the formula for cutoff frequency in case of rectangular waveguide. So that is FCMN. So cutoff frequency is equivalent to C by 2, not C, you can write V naught. Okay, so V naught by 2 into what? Square root of m by a whole square plus n by b whole square. Okay, so where V naught is equivalent to so this is the cutoff frequency for a rectangular waveguide here. So where V naught is equivalent to C by root over mu r epsilon r. Okay, so if a rectangular waveguide is air filled, okay, then in that case V naught is same as what? V naught will be same as C, that is velocity of light, right? Okay. So what is this cutoff frequency means? So in rectangular waveguide here, if the operating frequency is greater than this cutoff frequency, only those modes are going to be possible. Okay, only those modes are going to propagate inside the waveguide. So if the operating frequency is less than this cutoff frequency, then those modes are not going to propagate inside the waveguide. Okay. So here the rectangular waveguide is acting like what? High pass filter. So only the modes that are going to propagate inside the waveguide are nothing but what? If the operating frequency of a electromagnetic wave is greater than what? If it is greater than the cutoff frequency of a particular mode, then only those modes are going to propagate inside the waveguide. Okay, if operating frequency is greater than FCMN, the cutoff frequency of a particular mode, only those modes can propagate inside what? Inside a rectangular waveguide. Only those modes can propagate inside a rectangular waveguide, right? Okay. Next, if f is less than FCMN, right? So if the operating frequency is less than the cutoff frequency of any particular mode, then those modes are not going to propagate inside the waveguide. Those modes are going to decay inside the waveguide here. They are not going to propagate inside the waveguide. They are going to decay exponentially inside the waveguide. So here those modes are not going to propagate inside a waveguide. Those modes are not going to propagate inside the waveguide. Okay, so these modes right. Okay, so these modes, so you can write instead these modes are going to decay exponentially, inside the waveguide. Okay, so these modes we call them as what here? These modes we call them as, there is a name for these modes here. So these modes we call them as evanescent modes. We call them as evanescent modes. Right? So if the operating frequency is greater than the cutoff frequency of a particular mode, only those modes can propagate inside the rectangular waveguide. Okay, and hence we can say the rectangular waveguide is acting like what here? Rectangular waveguide acts as what? Acts as a high pass filter. Right? So it is going to allow the frequencies which is greater than what? Which are greater than the cutoff frequency. Only those modes are are possible to propagate inside the rectangular waveguide. So that's why I can say this rectangular waveguide is going to act like what? High pass filter. So if the frequency is less than the cutoff frequency of a particular mode, those modes are going to get attenuated inside the waveguide. They are not going to propagate inside the waveguide. Okay, so that's why I can say before this cutoff frequency, all the modes are going to get attenuated. After this cutoff frequency, all the modes are going to propagate. So that's why this rectangular waveguide is going to act like what? Is going to act like high pass filter. And the modes for which the operating frequency is less than the cutoff frequency, those modes are going to attenuate inside the waveguide. They are not going to propagate inside the waveguide. So those modes we call them as what? Here evanescent modes, right? Okay, evanescent modes, right? So I have given the formula for cutoff frequency, right? And most of all the other parameters are also going to depend upon this cutoff frequency only here. See, for example, if I write the expression for phase velocity, so the phase velocity is equivalent to V naught by square root of 1 minus Fc Mn by F whole square, right? This is the expression for phase velocity. And the group velocity, the expression for group velocity is nothing but V naught into square root of what? 1 minus Fc Mn by F whole square, right? Okay, so these are the expressions for phase velocity and group velocity here, right? Now see here, if you multiply these two, the phase velocity into group velocity, so what you are going to get? If you multiply these two, what you are going to get? So this term and this term will get cancelled. You are going to get what? V naught square. So V naught square. Okay, so if it is a air-filled rectangular waveguide, yeah, if I consider air-filled rectangular waveguide, then in this case V naught will become equivalent to what? C. So in case of air-filled rectangular waveguide, the phase velocity into group velocity is equivalent to what? Is equivalent to C square. Is equivalent to C square, right? Okay. Okay. And similarly, I'll give the expression for intrinsic impedance here. So intrinsic impedance in case of TE mode, is nothing but eta divided by what? Divided by square root of 1 minus Fc Mn by F whole square. See, the expressions for phase velocity, group velocity are going to be same either for TE mode or TM mode. Okay, all the formulas here, whatever the formulas that you are having in case of rectangular waveguide, all the formulas are valid for both what? TE mode as well as what? TM mode. So for both you are going to have almost all the similar formulas, but except for what? Except for intrinsic impedance here. So for intrinsic impedance, for TE mode you are going to have different expression, and for TM mode you are going to have different expression. For TM mode, the expression for intrinsic impedance is eta into square root of what? 1 minus Fc Mn by F whole square, right? Okay. Okay. So these are the expressions for intrinsic impedance in case of TE mode and intrinsic impedance for TM mode. So except for this intrinsic impedance, remaining for all the other formulas, it is going to be same for TE mode as well as what? TM mode, right? Okay. Okay. Right. Here where eta is equivalent to what? Where eta is equivalent to square root of what? Mu by epsilon here. Mu by epsilon. Okay. If it is air filled waveguide, you can replace eta with eta naught, that is square root of mu naught by epsilon naught, right? Okay. Okay. Right. And we are having the relation between the guided wavelength. That is I'll get that relation here. See, beta square is equivalent to, in rectangular waveguides, you are going to have all the field components here, that is x component, y component and z component, right? Okay, okay. So from here, what I am trying to get, okay. So here beta z is equivalent to what? Square root of beta square minus of what? Minus of beta x square plus beta y square, right? Okay. So where this beta square is nothing but what? Omega square mu epsilon minus of what? Beta x is nothing but m pi by a whole square plus n pi by b whole square. Okay, so this is the expression for a phase constant along net propagation direction here. This is the expression for phase constant along the net propagation direction. So this is the phase constant along net propagation direction. Phase constant along what? Along net propagation direction. Net propagation direction, right? So along this net propagation direction, we are going to define a wavelength which is called as guided wavelength. Okay, so guided wavelength is nothing but what? So beta z is equivalent to 2 pi by what? 2 pi by lambda, but here that lambda is nothing but a guided wavelength. So this guided wavelength is the wavelength that is defined along what? Along the net propagation direction. So this is called as lambda g is called as a guided wavelength here, guided wavelength. So guided wavelength lambda g is equivalent to what? 2 pi by what? 2 pi by beta z, 2 pi by beta z. So where beta z is nothing but what? Beta z is nothing but square root of omega square mu epsilon minus of m pi by a whole square plus n pi by b whole square, right? So this is the expression for a guided wavelength along the net propagation direction, right? Okay, okay. Right. Okay. So there is a relation between a guided wavelength and operating wavelength and cutoff wavelength. So I am giving that relation here. 1 by lambda g square is equivalent to 1 by lambda square minus 1 by lambda c square. Okay. So this is the relation between guided wavelength and operating wavelength and cutoff wavelength. So this lambda z is called as a guided wavelength, right? And this lambda is called as what? Is called as operating wavelength, and this lambda c is called as what? Is called as cutoff wavelength. So this is the relation between what? Between the guided wavelength and operating wavelength and cutoff wavelength. So these relations are very, very important here. Okay. So with the help of most of the questions are based on these relations only. So if you know cutoff frequency, you can determine almost all the parameters in case of what? In case of rectangular waveguides. Okay. Okay. So we'll try to solve some problems here based on these waveguides. right? Okay, so here let us consider this question. Let us take this question. So that is they have given in a rectangular waveguide, they have given in rectangular waveguide, they have given the expression for the electric field component here. So this electric field component they have given as omega mu by h square into what? Into pi by a, into pi by a, into h naught, into h naught, into sine of what? Sine of 2 pi by a into x, 2 pi by a into x, into sine of what? Sine of omega t minus beta z ay cap, ay cap. Okay, so here they are asking us the mode of the propagation. So what is the mode of propagation they are asking? What is the mode of propagation? The mode of propagation they are asking. So option A they have given whether it represents TE 20 mode or TM11 mode or TM20 mode or TE10 mode. So which mode it is going to represent? So this is the question they have asked here, right? So in rectangular waveguide, what they have given? They have given the electric field, the expression for electric field, right? The expression for electric field they have given, and from this expression they are asking us to determine the mode of what? The mode of propagation, to determine the mode of propagation. Now see here, if you observe here, this electric field is nothing but what? Y component of electric field. This is nothing but y component of electric field. Okay, so here if you observe, this represents what? This represents a standing wave pattern, sorry, traveling wave pattern. This represents traveling wave pattern along what? Along z, traveling wave pattern along z, right? Okay, and here this represents what? This represents a standing wave pattern. This represents standing wave pattern along what? Along x, right? So you are having only one standing wave pattern here, that is along x. You don't have any standing wave pattern along what? Along y, right? Okay, you are having only one standing wave pattern along x, you don't have any standing wave pattern along y, right? Okay, okay, so and here this is nothing but what? And here this is nothing but some constant, omega mu by h square into pi by a into h naught is nothing but some constant. So they have given some real time solution here, right? Okay, some constant multiplied by standing wave pattern along x. There is no standing wave pattern along y, and traveling wave pattern will be along z. So in that case, what is the mode? What is the mode? Whether it is TE20 or TM11 or TM20 or TE10. Okay, first of all you have to identify whether it represents a TE mode or TM mode. So we know that in TE mode here, in TE mode, okay, we know TE00 is not possible, whereas TEM0 mode is possible, right? Here m not equal to 0, and TE0n mode is also possible, here n not equal to 0, right? And here TEMN mode is also possible for m not equal to 0 and n not equal to 0. We know this one, right? Okay, similarly if you consider TM mode, so TM00 mode is not possible, we know that, and TMM0 mode is not possible, right, for m not equal to 0 and n equal to 0, and TM0n mode is also not possible, that is for m equal to 0 and n not equal to 0, right? And we know that TMMN mode is the only mode that is possible for m not equal to 0 and n not equal to 0, right? Okay, so I have already told that this m and n represents what here? M represents number of half cycles, number of half cycles of standing wave pattern along what? Along x, right? And n represents what? N represents number of half cycles of standing wave pattern along what? Along y, right? Okay, so if m not equal to 0 and n not equal to 0 means you are going to have both the standing wave patterns along x and y, right? If m equal to 0, n not equal to 0, okay, m equal to 0, n not equal to 0 means you don't have any standing wave pattern along x, but you must have a standing wave pattern along y. Okay, that's how you have to keep in mind here, right? So for m equal to 0, if m equal to 0, n equal to 0 means there are no standing wave patterns along x as well as along y. Okay, so now here t is 0 0 mode and tm 0 0 mode. Here m equal to 0, n equal to 0. Here also m equal to 0, n equal to 0. If both m and n are 0, so that means there exists no standing wave patterns along x and y. So that type of modes are not at all possible either in case of TE and TM, right? In case of rectangular waveguide, that is confirmed, right? And if you observe TE M0, here n equal to what? Here n equal to 0, here n equal to 0. Okay, here n equal to 0. So that means here m not equal to 0, that means you are going to have only one standing wave pattern. M not equal to 0 means you are going to have only one standing wave pattern along what? X. Okay, you are having only one standing wave pattern along x and you don't have any standing wave pattern along y. So that type of modes are possible in case of TE. And here also you are having what? A standing wave pattern along y, but you don't have any standing wave pattern along x, right? So this type of modes are also possible in case of TE. And if m not equal to 0, n not equal to 0, then you can have both the standing wave patterns along x as well as y. So this type of modes are also possible. When coming to TM mode, only one standing wave patterns are not at all possible in case of TM mode. Yes or no? So here m not equal to 0, n equal to 0. So if m not equal to 0 means you must have only one standing wave pattern in the along x, right? So that type of modes are not at all possible in case of what? In case of TM, right? So similarly TM 0n means you are going to have only one standing wave pattern along what? Y direction. So these modes are also not at all possible, right? So TM mode means you must have what? Both the standing wave patterns. TM mode means in TM mode you must have both the standing wave patterns, right? So whereas in TE mode only one standing wave pattern mode is also possible. Okay, here only one standing wave pattern is possible, here only one standing wave pattern is possible. So both the standing wave patterns is also possible. Okay, but here in the given expression they have given only one standing wave pattern here. So there is no another standing wave pattern, right? Okay, so only one standing wave pattern is possible only in case of what? Only in case of what? Only in case of TE mode. Only one standing wave pattern is possible in case of what? In case of TE mode. In case of TE mode. Whereas one standing wave pattern is not possible in case of what? TM mode. So that means we can conclude that this given expression or this field is nothing but what? Is nothing but the field of an TE mode. It doesn't represent TM mode because you are having only one standing wave pattern. Only one standing wave pattern is not at all possible in case of what? TM mode, right? Okay, so we can conclude that the given mode is nothing but what? The given mode is nothing but TE mode. That is confirmed, right? Next, here you are having the standing wave pattern along x direction. So this is just like what? This is just like m pi by a. M pi by a. So if you compare with m pi by a, m value is equivalent to what? 2. Yes or no? Okay. So here TE mn. So this is equivalent to TE. M value is equivalent to what? 2. And there are no standing wave patterns along y. So which means n is equal to 0. So that means the given mode must be what? Is nothing but TE20 mode. The given mode is nothing but TE20 mode. right? Okay. Okay, so the given mode is nothing but a TE20 mode here. Right? Okay. So the answer for this question is nothing but a TE20 mode. The answer for this question is nothing but TE20 mode. Option A is correct for this question, right? Okay. Okay. So next. Okay, so we'll try to solve one more question here. So that is next question. So they have given in an airfield rectangular waveguide, okay, cutoff frequency so in an airfield rectangular waveguide of cross section dimensions A centimeter, B centimeter, where A is greater than B, has a cutoff frequency of 6 gigahertz, for the dominant mode, okay, for the dominant TE10 mode, for the same waveguide, if the cutoff frequency for the same waveguide, if the cutoff frequency of the TM11 mode is 15 gigahertz, then cutoff frequency of TE01 mode in gigahertz is, okay. So this is the question they have given here, right? Okay, so in an airfield rectangular waveguide of cross section whose dimensions are given by A centimeters by B centimeters, where A is greater than B, so has a cutoff frequency of 6 gigahertz for the dominant TE10 mode. See, in a rectangular waveguide, TE10 mode is called as dominant mode here. So dominant mode means it is the mode with the lowest cutoff frequency. So the mode with the lowest cutoff frequency is called as what? Dominant mode. And in rectangular waveguide, TE10 mode is called as dominant mode. okay, because this mode is going to have the least cutoff frequency, right? So for the same waveguide, if the cutoff frequency of TM11 mode is 15 gigahertz, cutoff frequency of TM11 mode is 15 gigahertz, then what is the cutoff frequency of TE01 mode? TE01 mode in gigahertz is, okay, what they have given? They have given the cutoff frequency of TE10 mode, and they have given the cutoff frequency of TM11 mode. Then they are asking the cutoff frequency of TE01 mode, okay. So they have given the cutoff frequency of TE10 mode. So for TE10 mode, what is the cutoff frequency? FC10 is equivalent to, so the cutoff frequency they have given as 6 gigahertz, okay. So 6 gigahertz, right? Next for TE11 or TM11. So for TM11, the cutoff frequency they have given as 15 gigahertz. So for TM11 mode, they have given the cutoff frequency as what here? 15 gigahertz, right? Okay. Next, they are asking the cutoff frequency for TE01 mode. So they are asking the cutoff frequency for TE01 mode. So that is FC01. So this is what they are asking here. Now see here. So we know the formula for cutoff frequency here. So that is FCMN is equivalent to what? Is equivalent to C by 2 into. So since they have given here airfield, rectangular waveguide. So the velocity here I can represent, instead of V0, you can represent it as simply C. Okay, C by 2 into square root of M by A whole square plus what? Plus N by B whole square, right? Okay. So for FC10, they have given what? For FC10, they have given the cutoff frequency as 6 gigahertz. Okay, whereas for FC11, it is 15 gigahertz. They are asking us to determine FC01, right? Okay. So if you observe this here, I can write a FCM0 here. FCM0. What is the formula for FCM0? Put n equal to 0. What you are going to get? You are going to get MC by 2A. This is the formula for FCM0, right? Next, similarly, what is FC0n here? So put m equal to 0, then you are going to get what? NC by 2B, right? Okay. So now this equation, now if I send C by 2 inside here, what you are going to get? MC by 2A whole square plus what? Plus NC by 2B whole square. Okay, where MC by 2A is nothing but what? MC by 2A is nothing but FCM0, and NC by 2B is nothing but what? FC0n, right? Okay, so which means FCMN, I can write it as what? Square root of FCM0 square plus FC0n square, right? Okay, so FCMN, I can write it as what? I can write it as square root of FCM0 square plus what? Plus FC0n square, right? Okay. Okay, so here they have given the cutoff frequency for FC11 they have given, and FC10 they have given. They are asking us to determine FC01, right? This is what they are asking, right? So from this relation you can easily determine for FC01 or not. See here, if I take m equal to 1 and n equal to 1, then I can write FC11 is equivalent to what? Square root of FC10 square plus what? FC01 square, right? So from here FC01 square here, FC01 square is equivalent to what? FC11 square minus FC10 square, right? So what is FC11 square here? What is FC11 square? Tell me. So FC11 square is nothing but 15 gigahertz whole square. So that is 15 whole square minus what? FC10 is 6 gigahertz. So that is 6 whole square. So FC01 is nothing but square root of this one. So this whole thing multiplied by what? Gigahertz. So this is what you are going to get, right? So sorry, FC01, this is FC01. So FC01 is equivalent to what? So 15 square minus 6 square. So 15 square minus 6 square under root. Fifteen square minus 6 square is 189. Square root of 189, 13.74. So you are going to get a 13.74 gigahertz. Okay, so this is the answer for this question, FC01, right? Okay, so okay, right, okay. So in live nobody is there here. Okay, even I am feeling bored to teach you something, right? Okay, so that's why what I am doing here is I am ending up this session here. So I am not at all interested to go further, because if students are present, then I can teach in live. Otherwise it is no use of teaching in live here, right? So this is the end of this session. I am ending up this session, right? Okay, so instead of doing this live, I can record some lectures, so it is better, right? So unnecessarily it is a waste of time for me here, right? Okay, so if more students will come, at least some 5 to 6 students must be present now at least, right? Okay, so so there is no meaning of teaching in live without students here, right? So that's why I am ending up this session here, right? Okay, so I am ending up this session. So with this I am completing this complete revision of EMT. I am ending up this session here, right? I am not at all interested to continue this one. So instead of this I can do some recording work and all those things, right? Okay, so okay, then we'll meet again whenever it is scheduled, right? Okay, so until then, take care, bye bye, and thank you for watching.